Before starting with the two body problem, which is a part of the central force motion. So, let us look into the how the central force motion or the two body problem evolved. Okay. So, John Kepler, who was a student of Tycho Brahe, enunciated three laws, of which first two appeared in Astronomia Nova in 1609. Later he published Harmonics Mundi Lec-05 means harmony of the world, and the third law appeared here along with other 13 theorems. So, and these three laws are popularly known as Kepler's law. So, Kepler's laws, which are three in number, can be written as the first one, the orbit of each planet is an ellipse with sun at one focus. The line joining the planet to the sun sweeps out equal areas in equal times. The third law, it states that the square of the period of a planet is proportional to the cube of its mean distance to the sun. Okay. So, Kepler's law, it captured the kinematics of the motion. So, Kepler's law, it captured the kinematics of motion of evenly bodies which were inferred from observations made over a long period of time. But the dynamics of the motion remain unresolved, but the dynamics of motion remained unresolved until Isaac Newton unlocked them. So, Newton enunciated three principles or the three laws which are popularly known as the Newton's three laws, okay. And he enunciated these laws in his book Principia. So, Newton enunciated three principles in 1687 in his book Principia. So, these three laws, so out of which the first law, it states that every body continues in its states of state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. Okay. So, we will discuss further about implication of these laws. So, the first law is every body continues in its state of rest or of uniform motion in a right or the straight line. Unless it is compelled to change that state by forces impressed upon it. The second law, it states that the change of motion, is proportional to the motive force impressed and is made in direction of the straight line in which the force is impressed. The third law, it states that to every action there is always an opposite and equal reaction, or alternately we may state that the mutual actions of two bodies upon each other are always equal and directed to contrary parts. Okay. Now, the Newton's second law, you will see that this leads to the first law, but the question arises, was Newton wrong or he did some mistake in enunciating the first law? If the first law can be derived from the second law, then what is the need of the second law? Okay. So, let us look into the second law, it is a mathematical formulation. So, second law can be stated as the force impressed. So, rate of change of momentum will be proportional to the force impressed. Another way we can write F is equal to k times dp by dt. So, here mass is assumed to be constant. So, for the second law, mass is assumed to be constant. So, this can be written as k times d by dt mb. M times A, where A is acceleration, P is linear momentum, M is mass, and T is time, and K is proportionality constant. In SI system, for 1 Newton of force imposed, and for a unit mass that is 1 kg of mass, if the resultant acceleration is taken as E is equal to 1 meter per second square, okay. Then this implies k is equal to 1. Okay. So, the second law can be written in this format, F is equal to m a. Now, suppose we put a equal to 0. So, this implies f equal to 0. In other words, if a particle is moving along x coordinate axis, then we can write m times or d square x by dt square, f is equal to m times d square x by dt square, this is equal to 0. Okay. So, in turn this implies that dx square x by dt square, this is equal to 0, which implies dx by dt, this is a constant. Okay. So, this dx by dt we can write it as v, which is a constant here. So, if this constant is 0, okay, if the constant v is equal to 0, then what we see that a particle which is moving which is initially at rest will remain at rest until unless a force is applied, because here the f we have set to 0 means no force is applied, and therefore, if the particle is initially at rest, so it will continue in the state of rest. Now, if v is not equal to 0 initially, so this implies that particle will keep moving with the initial velocity until unless an external force is applied. Okay. So, in another way we can say that from the Newton's law we have obtained the first law, which states that if a particle is initially at rest or is moving with constant velocity. So, it will continue in that state until unless an external force is applied. Okay. Then as earlier I mentioned, then the question arises whether Newton did some mistake or this first law was not required at all, because it can be derived from the second law itself. Then what is the need of the first law? The reason is the second law, it gives only the mathematical aspect, that if the external force is applied, so how the change will proceed. Okay. It does not say anything why this until unless we apply an external force, why the change in a state is not taking place. It does not talk about that. So, the first law talks about that, and therefore, it is a most often it is called as the law of inertia. Okay. So, this is the reason the first law has been enunciated. Without first law, Newton's fundamental postulates about the mechanics would have been incomplete, because without inertia we cannot describe why a system is behaving or it is resisting to the motion to the externally applied force. Okay. Or in the absence of the externally applied force, it is not changing its state. Okay. So, it is because of this inertia. This can be we can give an explanation to this. Okay. Suppose we have two objects, one is heavy and another one light, and both are resting on the floor on a frictionless floor, and then we try to move both the objects. So, obviously, once we try to move the both the objects, we feel we have to apply more force to the heavier object than to the lighter object. Okay. So, the reason is why we feel why we have to apply more force to the heavier object, it is because of the inertia. So, inertia is a property of mass, this is not the mass itself. Because of the mass, this inertia exists, which tends to resist the motion of the object or the motion which results from the external applied force. Okay. So, let us write little bit about this. So, two objects one light and another one heavy. Light one requires less force, while the heavy one requires large force. So, this is because due to inertia, so this we are discussing about an object on frictionless surface. Okay. So, because of this is because of inertia, and due to inertia both objects resist motion. Originally both objects are at rest. Hence, having no linear momentum. Thus, the resistance is totally due to inertia. So, the first law we will call as the law of inertia. So, inertia is a property of mass, but is not mass itself. So, starting with this preliminary ideas about the central force motion and the Newton's law, then we start about the we start with the mathematical formulation of the central force motion. Before going into the two body problem, let us consider that there is a center of attraction, and a particle is moving under the field of that attraction. So, we have here the central force motion So, what are the characteristics of central force motion? We try to derive them mathematically here in this place. So, the first characteristic can be stated as the central force motion occurs in a plane. Let C be the center of attraction and some particle of mass m is moving under this attraction. So, r is the radius vector to the particle m and F is the force acting on the particle m, then the moment acting on the particle can be written as m is equal to r cross f. We can see from this figure that f and r are collinear. That is, angle between f and r, it is a 180 degree. That is, angle between f and r is 180 degree. Therefore, the cross product will vanish. Okay. So, this we can write as magnitude of m we can write as magnitude of r times magnitude of f times sin theta. So, here theta is the angle between r and f. So, theta in this case is 180 degree, therefore, the magnitude of the moment it becomes 0. Now, m can be also reduced to a different format. So, we can write this as d by dt Now, d by dt r cross m b can be written as dr by dt cross m v plus r cross m dv by dt, or we can write m inside the bracket itself. Now, dr by dt here, this is nothing but v. So, this is a cross product v cross m cross v, m is a constant, therefore, this quantity becomes equal to 0. Therefore, we can write m is equal to r cross d by dt, m b is equal to d by dt r cross m b. Now, r cross m b this is nothing but the angular momentum and this we can write as say h. Okay. Therefore, m can be written as dh by dt. Okay. So, for planar motion, we can write m is equal to r cross f equal to 0 is equal to dh by dt. So, this implies h is equal to a constant. So, that is in central force field angular momentum of a particle is constant or conserved. So, this is the first property, that the angular momentum will remain conserved, and moreover, because we have seen earlier in the last slide, this is m is equal to r cross f. Okay. So, here this is coming to be a 0, and the ultimately the h vector we are getting this as a constant, means the particle is moving in a plane. If the angular momentum vector is changing, then the motion of the plane, it will continuously change. Okay. If angular vector, if the angular momentum vector is a constant, means angular momentum will be as it is defined here, this is r cross m b. So, here the angular momentum vector will be perpendicular to the both r vector and the velocity vector, both to the radius vector and to the velocity vector. Therefore, and this turns out to be a constant, therefore, the r and v vector, they will always lie in a plane. So, the second characteristic of the central force motion is that the energy is conserved. Okay. So, total energy is conserved in central force motion. Or the central force motion, we can write central force motion is conservative. So, total energy remains constant in central force motion. So, let us consider the center of attraction C and a particle which starts from point A and moves to point B along certain path. So, the radius vector to A can be written as R A and radius vector to B can be written as R B. So, work done in taking the particle from A to B can be written as W A B equal to R A R B, the limits F R so force is a vector, and The work is defined as the dot product of the force and the displacement. Okay. So, now we can write F r is equal to okay. So, the force is acting because it is a central force motion, the force is directed toward the center. Okay. So, this is the F r. Now, we can write d r dot r to r dot d r. So, differentiating this results in 2 so, left hand side we can write as d r square is equal to 2 r dot d r, or other way we can write 2 r times d r is equal to 2 r dot d r. So, this gives us r d r is equal to r dot d r. Okay. Now, we can use this and put it into the equation 1, the equation A, and let us say this is equation B and term this as equation C. Okay. So, using equations A, B and C, can write W A B is equal to so this can be written further as F r by r times r dot d r. Okay. So, using equation C, we can write this as r a r b F r by r times r d r. So, these two cancel out and this leaves F r d r, r a r b. Thus, we see that W a b is a scalar function. Because the integrand does not depend on path. Which is obvious. So, we can drop the vector notation here and just keep that it is a moving from point A to point B. So, the integrand being the scalar function, we can define W a b as R a to R b, and we can define a function what is called the potential function, which we can write in this way. Okay. That is du r minus du r is equal to f r dr. So, this implies du by dr is equal to minus f r. Okay. Because we have seen that the integrand it is just a function of r. So, it is a scalar function. So, once we integrate it, so the after the integration the function that we get that will just depend on the value of r. So, therefore, it is a we can replace in terms of a potential function, which is we have written here as u. So, here u is the potential function, is a potential function So, we have f r dr W a b, this is equal to f r dr, and between R a and R b minus du r R a R b. So, this can be written as u R b minus u R a with a negative sign. Okay. So, this is equal to minus u R b plus u R a. Further, we can write f r dr, we can express this as m times dv by dt. So, using Newton's law, we can write this f r dr okay, or directly in the scalar notation also we can write m dv by dt, and then so let us put this as so here f r we have put as this quantity. If we try to put here the vector notation, so this will be f r dr in this format m dv by dt, and then here we will have a dot product, okay, and this we can write in this fashion. Okay. So, then this becomes equal to now dr by dt, this is dr by dt is nothing but v. So, here we have m dv by dt, then dot product v dt and integrating it. So, this we can further write as, because m is a constant, we can take it outside the integration sign, and this becomes v dot dv. Okay. And then putting the limits of integration from R a to R b, so instead here the limit of integration we can change and write this as V a to V b. Okay. And this is very simple to integrate. So, f dot dr R a to R b, this is nothing but f V a V dot d v. And integrating this can be written as m b square by 2 So, this is easy to see here. Let us write this as d v dot v. So, this will be equal to d v dot v plus v dot d v or 2 v dot d v. Okay. Therefore, this implies v dot d v, this is equal to 1 by 2 v dot v. So, 1 by 2 v square. Okay. So, after writing it in this way, we can expand it and write it v square times m v a square by 2. This is our equation number D, or we write this as the equation number E, and we have the equation number D in this place. So, from equation number D and E, from equation number D and E, we can write m v b square divided by 2 minus m v a square by 2, this is equal to minus u r b plus u r a. Okay. After rearranging, we can write m v a square divided by 2 plus u r a, this is equal to m v b square divided by 2 plus u r b. So, this is our equation number F. Thus, we see that from equation number we can conclude that the kinetic energy plus potential energy at point A is equal to that at point B. Okay. So, therefore, this implies that the total energy which we can total energy here is nothing but the potential energy plus the kinetic energy. So, it remains as a constant. So, therefore, this implies in central force field total energy of the particle remains conserved. Wind up. Okay. Now, the third law of the third characteristic, the here the third characteristic of the central force motion is aerial velocity is constant. That is, aerial velocity is constant. That is, area swept by the line joining the center of force and the particle sweeps out equal amount of area in equal time. And this is very easy to deduct. Suppose again C is the center of attraction, and here some particle is moving in a path. So, we have the radius vector at point A as r a, and or let us write this as r, and in time delta t, then it moves by amount some delta r. So, the quantity, the radius vector of the particle then becomes, so once it comes to the point B, so it becomes r plus delta r. Now, if we have this kind of diagram, so we can find out the area of content within this figure. So, let us indicate this angle is delta theta. Okay. So, we have this vector, another vector is this one. So, this is r and this is r plus delta r, this angle is delta theta. So, we complete a parallelogram. Okay. So, this is the area we are concerned with. Okay. This is our delta r. So, area of the parallelogram can be written as say the total area of the parallelogram, area of this will be r cross r plus delta r. So, the shaded area then becomes equal to 1 by 2 times r cross r plus delta r, and this is nothing but the delta A area which is swept in time delta t. So, the rate of swept of area in time delta t, this can be written as 1 by 2 r cross r plus delta r delta t, or 1 by 2 delta t times r cross r plus. So, this quantity equal to 0 because it is a cross product, and therefore, delta A by delta t becomes equal to 1 by 2 r cross delta r by delta t. So, this is nothing but 1 by 2 r cross delta r by delta t as the in the limit delta t tends to infinity 0. So, we can write here delta t tends to 0. This can be written as r cross v. So, this we can write as r cross m b divided by m. Okay. So, this is 1 by 2 and r cross m b is nothing but the angular momentum of the particle, or this is h by 2 m. So, already we have seen in the first characteristic that h is a constant, therefore, d a by d t this becomes constant. This follows from first characteristic.